like to introduce Hong Lu from MIT. Hong finished his PhD at Case Western in '97. He was then a postdoc at Imperial College and then Rutgers, and has been at MIT since 2003. His work is impressively varied and broad. He worked on very stringy physics, and more recently on more down-to-earth topics. And today he's going to tell us about a modern take on hydrodynamics.
Okay. Thanks, Amos, for the invitation, and it's a great pleasure to be here. Today I will talk about hydrodynamics. Of course, the fluid phenomena are ubiquitous in our lives. It's very important for the existence of life. It also affects our daily life, and also it's important for what's happening inside the Earth, and also etc. And it's also very important for the Sun, and for the galaxy formation or form of the large-scale structure, etc. Hydrodynamics, surprisingly, let me just say, of course, the hydrodynamics has a long history, and dating back to at least 200 BC, and many people have developed things, including Da Vinci, Newton, Euler, etc. And the basic idea of the hydrodynamics is so-called the fluid picture. So it imagines the fluid as a continuum of a fluid element in local equilibrium. So what this means, let's look at the fluid flow, and so let's just, you can see that any point in the fluid flow should be considered, as a fluid element. So each fluid element corresponds to a point. And you should imagine this point actually corresponding to a collection of a large number of microscopic objects, say molecules. And they interacting with each other very quickly, and so they are always in the local equilibrium. Okay? And but since we cannot resolve them, and we just treat them as a single point, and then the fluid will be just a collection of such kind of fluid elements. And there's two ways of thinking about fluid. So one way, so-called the Euler way, is to just consider a single point or single fluid element, and then associated with that point, then you can define the number density, the particle density, the local temperature, and the local velocity, etc. The reason you can define local temperature is precisely because there's a local equilibrium. And this alternative way to think about it is that you follow fluid element. So that the fluid element, then the fluid element will flow, and then you follow each fluid element. And so this is called the Lagrangian way. And in the Lagrangian way, you put a label, say sigma I. Since this fluid element fill the whole space, and then this just this is again some three-dimensional coordinate, and then you associate each fluid element with a label, and then this label just goes with each fluid element. Say for example along this right line, which is not very clear here, and then the sigma remains the same. Okay, and in this Lagrangian way, and then there's a mapping between these fluid elements to the space-time coordinate, and then this mapping describes how this fluid element moves in the space-time. For example, this particular trajectory, and then can be described as a function. Okay, and then associated with each fluid element, then you can introduce the number density or the local temperature, etc. Okay, these two ways of course, are equivalent to each other, and they provide a complementary way to think about fluids. And the fluid, to describe the hydrodynamics, what you do is that you express your energy momentum, say in terms of these variables, from our standard, just from your based on physiological observations, you can express energy and momentum in terms of those variables at the side, and then the equation of motion for hydrodynamics are essentially just the energy or momentum conservation and the continuity equations.
Yes. Just to avoid confusion, this I subscript I at S and then sigma take a different meaning, right?
Oh yeah. This is a dummy. Here is a dummy variable. So they all run from 1 to 3, and they do have different meanings. Just for simplicity, I use the same thing. They all run from 1 to 3.
Sigma I on sigma 1 it's just labeled a particle. It labeled some particle whose motion you follow.
But the particle is particle fill the three-dimensional through three-dimensional space. And so you actually have a three-dimensional label for the particle.
Why is there no velocity on the right-hand side?
The velocity just can be obtained by taking this derivative with t, and then this is just corresponding to the trajectory of this particle, and then when you take the derivative with t, then you just get the velocity. This is just a different ways to think about it. This is a very important question because at this point will be important. So the hydrodynamics is very simple. Just the energy and momentum conservation, and nothing else, and then the inputs are this how you express energy momentum in terms of those so-called fluid variables. So surprisingly, hydrodynamics also has made unexpected entries in the 20th century physics. And in many situations which quantum mechanics play a very important role. And so the example which I mentioned earlier, they're all related to classical physics, etc. But they also, hydrodynamics also have a very important role in quantum dynamics. In quantum systems. So here we quickly describe 3 examples, all related to the physics of the last decade, which hydrodynamics plays a very important role. So the first example is so-called quark plasma. So if you consider the strong interaction at the room temperature due to so-called the quark confinement, because the interaction between the quark and gluon is very strong due to so-called the color confinement, and the quarks and gluons are always confined inside the colorless objects, say hydrogens, including protons, neutrons, ions, etc. But now if you heat the system to very high temperature, and then eventually the hadrons will be melted, if you, because now you have sufficiently kinetic energy so that those quarks and gluons can escape from the confinement. So what you get, so the quarks and gluons they become deconfined, then they form so-called quark plasma, and they can essentially freely roaming around in this plasma. And so this is a new phase in QCD, which you can only achieve, say, by going to sufficiently high temperature. And during the last decade, since the beginning of the 2000s, people have been trying to collide heavy ions to create the quark plasma. So this is, say, using the relativistic heavy ion conditions. So the basic idea is very simple. So you take the 2 heavy nuclei, say for example here is a 2 net, So you accelerate to very high velocity, and then you just collide them. And then in a very short time, those high energy, when they collide, and those high energy will essentially create large number of particles, and then they will thermalize, and then create very high temperature. And then that will essentially melt, say, the nucleons inside this net. And then you will form a quark plasma. and eventually the quark compartment you form is not static. It's like a little universe. They will expand, and then they expand, and then just like a universe, they cool. And when they cool, and again they will hydrolyze. Okay, when they cool sufficiently, they will hydrolyze. And so in the detectors, then yeah, so the typical size of this quark plasma, say it's roughly the size of the this nucleus itself is around 14, say meters, and then they last very short time. Okay, they quickly expand, and then they cool, and then hydrolyze. So this quark plasma exists very short time and reach very high temperature, and this is essentially the highest temperature one can reach, say on Earth. And so in the detector, what you observe is just thousands of particles. Okay, and so this way hydrolyze again thousands of particles you detect in your detector. Okay? So it turns out, so the key of this heavy ion collision physics is by looking at the detailed information of those particles recorded in your detector, try to deduce the dynamics of this quark plasma. Okay, deduce the evolution and the properties of this quark plasma. Okay. It turns out, in order to explain the correlations, so you have so many particles recorded in your detector, and turns out those particles actually they correlate. Okay, different directions they correlate. So it turns out in order to explain the correlations of the detected particle, one finds that the evolution of the quark plasma after its creation should follow hydrodynamics. Say, as if you assume that after the quark plasma was immediately produced, and their evolution actually follows from hydrodynamics, then you can actually naturally explain the data. And you can explain the data very well. Okay, you can explain the data very well. So this gives you very strong support that actually the quark plasma produced actually behaves like a fluid. Okay, behaves like a fluid. And in fact, it behaves like so-called perfect fluid. And because the quark plasma produced actually have very small viscosity. For example, compared with water, and it's yeah, so it's like what normally called perfect fluid. Okay, so now let's move out to a second example, and this is the graphene. So graphene was discovered during the last decade, and for the Nobel Prize. And so this is a single layer of carbon atoms. They arranged in this kind of pattern. Okay, and in the graphene, of course, the electrons, etc. And normally, when you have a metal, electrons in the metal can be thought of as a positive particle, and they move ballistically. Okay, so for example, if they have some impurities, which you often have in the metal, and then the electron will collide with those impurities just like a billiard ball. Okay, it's a ballistic. But it turns out, surprisingly, people just found last year that the electrons in the graphene actually behaves again like a fluid, like some water. Okay, and if you have some kind of impurity there, and the electrons actually flow around it. Rather than collide with the impurity, okay, it actually flow around it. So this is a cartoon, and for the liquid. So here is a smoking gun experiment to show that actually electrons in the graphene actually behaves like a fluid. And this is the experiment suggested by my colleague Lemitov and also Fokovich at the Weizmann Institute. And so the basic idea is very simple. Imagine this is a graphene, okay? And now at one side, so this is just a layer of graphene. And imagine here you infuse, you inject, say, a current into the system. Okay, and then here you have a drain. Okay, so the charged particle will just move from outside. Okay, so if they just say as ordinary for the electrons in the metal, say they move ballistically, then you can easily show that the potential distribution for this material will be like this. And so you have a positive. Yeah. So if you measure the potential difference between the upper side and lower side, then you here is a positive potential and this is no negative potential. Okay. But
so it is a point sources at the top and bottom.
Yeah. You can imagine it's just some kind of you can imagine some kind of point source. So now, suppose the electrons behave like fluid, then the very different thing can happen. Because when you have if it's a fluid, then there's a viscosity. Then typically you will form this this kind of vortex kind of behavior. And then you can just do a very simple calculation to solve the equation. And then you find actually the behavior becomes very different from this case. The near the source, actually near the source, because of this kind of backflow, then the upper layer actually near the source actually have electric potential compared to the lower, instead of this in the what you expected in the ballistic case. Okay, so this is what heuristic, what people call say elective resistance, because it's reversed. Okay. And so if you measure this, then that will be a smoking gun for that actually electron behave like force. Okay? And this experiment, so this was published in the Nature Physics in February 2016. And then 1 month later, a GAMS group in Manchester, so they published in Science. Indeed, they precisely did this experiment. So they followed the suggestion, they did this experiment. They indeed they find this this kind of electric local resistance, okay, due to the electron backflow. Okay, and so this suggests that the electrons in the graphene actually behaves again like liquid. Okay, and now this is my third example, and this is actually called Fermi gases, say produced in the autonomous group. And so this is so this color shows the density of the atoms. So in the middle, it's the highest, and then here there's essentially no atom. Okay, so you use some kind of you use laser and other kind of techniques. You can lower the system to very low temperature, and then you can also confine to this kind of shape. So this is a cigar shape, large fermionic lithium-6 atoms. And again, using technique, you can turn on some magnetic field, and depending on the strength of the magnetic field, you can actually tune the interaction between those atoms. Okay, it's a highly tunable system. For example, if you tune the scattering length to infinity, and then you can reach so-called the Fermi gas at parity, and then those atoms will be very strong interaction. So now you can consider the following again. Consider the following experiment. So let's imagine you create a cigar-shaped material like this, cigar-shaped or this called atom gas like this, and the trap. And now suppose you release the trap, okay, and just let the atoms to be free. Okay, release the trap, and then of course those atoms will move out. Okay, those atoms will move out. So if those atoms again move ballistically, and then because there are many atoms here, and then they will move in random directions, and soon, and then you will lose the track of the initial shape. Okay, it will be approximately be spherically symmetric. Okay, just because of the large number theory. Okay, but instead, what this John Thomas group found is the following. What they found is following. So they find actually instead, they find that in the longitudinal direction there's not much motion, but in the transverse direction there's expansion. Okay, so essentially expand in this direction. You expand, 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 expand. So this direction there's nothing going on. Okay, and then we'll expand more, and this part already, yeah. Anyway.
But this is because they are confined strongly in that direction, the transverse direction.
Yeah. That's the important point.
In that direction.
So,
in that direction, nothing happens.
So this behavior again suggests a liquid, because this is a typical of a liquid. Because in the liquid, say suppose this is just a gas of atoms, and then the pressure at different points then will be uncorrelated with each other, and then there's no reason for atoms not to move in those directions. Okay, but now if this is a liquid, and then you would have a equilibrium in the pressure, and then that means in this direction, because the pressure is zero outside, and say some pressure in the middle. And again, it's zero outside, but the same pressure at the middle. So that means the pressure gradient in this direction is much larger in that direction. And since pressure gradient in this direction is much larger, and then you only expand in this direction. Okay? So this is typical of a collective behavior of a liquid. So in order to have this behavior, you have to have some kind of collective behavior. This won't happen if all the atoms here move randomly unrelated to each other. Okay? And again, this behavior can be nicely described, say, by hydrodynamics. You can really simulate this behavior in hydrodynamics. In fact, this behavior is also precisely what happens in the heavy ion collision. So in the heavy ion collision, when you collide two nuclei together, normally they are not perfectly oriented. And then two nuclei, they will overlap again in this kind of element-like shape. And then precisely, and of course in the heavy ion collision you cannot take the snapshot, okay? But the final, but this kind of expansion will show up in the correlations of your final plot the particle which you detect in your detector. And precisely, and this kind of correlation happens in the heavy ion collision. Okay, and so actually precisely the same kind of physics happens. Anyway, so here again suggests the hydrodynamic flow of some closed dome gases. So now we see 3 examples. Okay, and they range in very different materials. Okay, so here is carbon plasma, which they impact the strong interaction. So this is essentially the highest temperature you can find in the we made so far. This is 10 to the 12 K. And here is the strong interaction, and here is Coulomb interaction. Okay, Coulomb interaction. This is the room temperature, and the vice. And here is essentially the atomic interaction, some short-range atomic interactions. And this is essentially the coldest temperature you can find on Earth. Okay? So over a whole range of temperatures, all different type of interactions, somehow hydrodynamics got involved. Okay? Hydrodynamics got involved. So why is hydrodynamics so effective? Okay? And all of them look nothing like water. Okay? So why somehow hydrodynamics required? So I call this unreasonable effective hydrodynamics. Okay. But actually, sorry. I should hide. Yeah, this is supposed not to show here. Okay, but turned out there's a very simple reason for it. It turned out there's a very simple reason for it, and as follows. Okay, so let's consider. We have some kind of non-wavelength disturbance of the system in some equilibrium. Okay, and so this is a non-wave disturbance. And suppose this system have a very short, by non-wavelength, we mean that the variation of the density or temperature exactly is much larger than a typical mean-free path. Okay, typical mean-free path. That's symbolically drawn here. This is much smaller than that. Okay, and so in such a case, and then since happens very differently, depends on what kind of disturbance you create in your system. Okay? So if the disturbance is in the non-conserved quantities, and then at each point in space-time, those disturbance can relax locally. Okay? And then quickly, so every point they can relax at the same time. So the quickly, no matter what is the wavelength of this, and you can, in a very short time, just a typical mean-free time, and then this disturbance will be relaxed, and then you will come back to quickly, very quickly. Okay, yeah, the mean-free paths and the mean-free time are very short. So if we are thinking about molecular scale, these are scales very short, which we cannot detect normally. Okay. But on the other hand, if it happens to conserved quantities, but because the conserved quantities are conserved, due to the conservation, they cannot be relaxed locally. They can only relax via the transport. Okay? Suppose, say you have some charge density imbalance, and the charge density then cannot be destroyed locally. They can only be transported from one place to the other. The only way to achieve equilibrium is for the extra charge density here to be transported into charge density here. Okay?
What are the conserved quantities and what are the non-conserved quantities?
Yeah, 1 second. Yeah. And then we finish this. I will mention that. So if you have some conserved quantities, for example, charge density, and then they can only, the only way to achieve equilibrium is to transport from this excess to the deficit. Okay. And then say we'll take. Then when the wavelengths become longer and longer, then we'll take longer and longer time to do this. Okay, so the long time scale physics will be solely dominated by the dynamics of conserved quantities, because no matter what kind of disturbance you have for non-conserved quantities, they just immediately washed out. Okay, so conserved quantity, for example, energy, momentum. So if you have a charged particle, then the charge density, etc. And say in the wrong relativity case, also the particle density, and those are just only those quantities. And the non-conserved quantities, you can do many things. For example, activation, etc. Okay. Good. So that tells you that when you take the wavelength to infinity, then relaxation time must go to infinity. Then at the large distance and long time, the only relevant physics. So if we're interested in the long time physics, say so the length scale much larger than the mean-free path, and the time much larger than the mean-free time, which is normally the kind of physics we're interested in, and only the dynamics of conserved quantities are relevant. Only the dynamics of energy momentum conservation, the charge conservation or particle number conservation are relevant. All other details are washed out by the fast interactions, and they don't play any role at long distance or long time. Okay, and they're just not relevant. Those details are not relevant. Okay, and so this tells you that the hydrodynamics and remember at the beginning we said hydrodynamics is precisely the physics of the conserved quantities. Hydrodynamics is the description of the energy momentum conservation and the particle number conservation. Say there can be doing equation. Okay. So this tells you that the hydrodynamics is the universal theory for non-equilibrium dynamics of all many body systems at sufficient long distance and times. So if you have sufficient long distance and times, and when all the short distance physics are washed out, and these are the only things relevant. Okay. So now this naturally explains why for those diverse, so the hydrodynamics is the universal law of effective theory. Okay. So this naturally explains why, for such diverse interactions and so different systems, somehow hydrodynamics govern them all. Okay, govern them all. And not only that, and the fact that hydrodynamics works for those systems actually tell us very important information about those systems. as I said, this program plasma created, say, I'd say at RIC or LHC, they have very short lifetime. Say they last only 10 to the minus 23 seconds. So, and their size is about 10 to the minus 14 meters. So now in order for hydrodynamics to apply, it must mean that the interaction among the quark and the gluons in this deconfined state must be so strong, okay, so strong, that even at such a very small scale, at the time of 10 to the minus 23 seconds, it's still much, much longer than the typical relaxation time, okay, typical relaxation time. So this tells you that this program plasma must interact very strongly, okay, must interact very strongly. And so this is actually very much contradictory to people's to people's surprise at the beginning, because people expected when you create a program plasma, then it behave like some quark-gluon gas. So they don't expect such a strong interaction between the quark-gluons still at such temperatures. Okay, and so this gives you an important clue. And similarly, this is the graphene. So the reason that the graphene actually the hydrodynamics applies, but not in the ordinary metal, is because in the graphene you can make graphene can be made to be very, very pure, and then essentially you don't see impurities in graphene, or the impurities are very, very far away. And then instead, in ordinary metals are dominated by the electron impurity interactions, but in the graphene we are dominated by electron-electron interactions. And so that's electron-electron interactions that give you this kind of fluid metal. Okay, but in ordinary metal, because the impurity is very highly concentrated, and the electrons don't have time to interact with each other, and then you just see the ballistic behavior with impurities. And similarly, in this called atom systems, again you can here you tune the magnetic field for them to be strongly interacting, and then you find indeed the hydrodynamics of the works. Okay, and so hydrodynamics also tells the fact hydrodynamics works for those systems also tell us actually they are strongly interacting quantum liquids. Okay, so these are actually examples of strongly interacting quantum liquids, and then okay, so the hydrodynamics is remarkably powerful. Not only in the traditional physics, but also in the modern particle physics, nuclear physics, and matter physics, etc. Okay, but despite this long glorious history of hydrodynamics, method-based hydrodynamics have some defects. Okay, and one of the most important defects is that the hydrodynamics formulated as equation motion, because it's just a conservation of the energy moment. It's a equation motion. But as we know, that when you solve something just by equation motion, it's deterministic. There's no fluctuation. Okay, since it not fluctuates. So the hydrodynamics, as you already formulated, does not capture fluctuations. Okay, it does not capture fluctuations. But there are always fluctuations. Okay, there are always statistical fluctuations. There's fluctuation in this room. The room temperature fluctuates. The air density fluctuates, etc. Okay, so even though this is the kind of thing we want our students to forget when we teach them thermodynamics, but there's always fluctuations. And there are always thermaloids. Thermaloids are everywhere. Okay, and they if you just take a piece of wire and then there's a thermaloid, you can measure the thermal current into the noise. Okay. So the fluctuations are everywhere. And they are also important in many physical contexts. They are also very important in many physical contexts, for example, in the transport. And the fact that there are hydrodynamic fluctuations can affect your conductivity, viscosity, etc., can affect your transport. And also dynamic aspect of phase transitions, non-equilibrium state, turbulence, etc. Okay, so there are many places the hydrodynamic fluctuations actually play a very important role. But so far, we can only treat them, we either could not treat them or treat them phenomenologically near the equilibrium. And in far from equivalent situation, then we don't know how to do. Okay, there's no systematic way. So now let me give you two examples. Just two examples. Low temperature quantum fluctuations also important. So let me just give you two examples which the hydrodynamic fluctuations actually play a very important role, and understanding them will help a great deal for understanding those systems. So one example is so-called the non-equivalent phase transition. Okay, and the simplest example is very old for the Rayleigh-Ballard problem. So simply said, the Rayleigh-Ballard problem is like this. Suppose you consider a tank of fluid, and you heat some temperature at one temperature at the bottom, and put some other temperature at the top, with the bottom temperature is higher than the top temperature. And when the temperature difference is small, and then what you get is just some kind of temperature gradient. In this fluid, okay, it essentially just established a temperature gradient. And this is a non-equivalent steady state, okay? Yeah, this is non-equivalent state. Yeah, even the last book is still a non-equivalent state because there's a heat flux. But now, suppose you increase the temperature difference between them, just like when you boil your water, then something happens in every day when you boil the water will happen. It's at a certain point, then there will be convection. Okay, the convection will develop. And so the onset of this convection then pretty much behaves like a second order phase transition. Okay, but this is a non-equivalent phase transition. And this phase transition essentially is driven by the hydrodynamic fluctuations. Okay, driven by hydrodynamic fluctuations. So currently, we only know how to treat this kind of thing in the some way mean field approximation. Okay, it's just like the old days before the Wilson treated the phase transition as mean field approximation. Right now, our treatment of this kind of non-equivalent phase transition is more like a mean field transformation. But if you have a theory of the fluctuation, general theory of the fluctuation dynamics, then you will be able to treat this just treat the fluctuation for more fully. And another example is in the carbon plasma in the Havian conditions. So as we know, the statistical fluctuation is inverse proportional to the system size. When the system size is very small, the statistical fluctuation can be significant. And for example, for such a small system, and you expect statistical fluctuation to be significant. Okay, and that may account for how you explain the data in the factor. But more importantly, the hydrodynamic fluctuations will play a key role in the next decade when we start searching for the QCD critical point. So this is a QCD phase diagram. So the vertical axis is the temperature, and the horizontal axis is the baryon mechanical potential. So right now, the Havian condition has been forming around this region. So you create some quark plasma at some temperature, then eventually cool down, then the hydrolyze, and then you detect them. Okay, so it's very small kind of baryon mechanical potential. But we believe actually in this phase diagram somewhere there's a critical point. Okay, somewhere there's a first order phase transition separate between the quark plasma and the hydrogen gas, and then this because here is a crossover. And then there must be a critical point somewhere here. And the location of this critical point is not known. Okay, but in the next decade, at Brookhaven, people are going to search for this critical point using Havian conditions. So what are you going to do? So you just now create quantum plasma with different chemical potential. Okay? But now the key or the critical point is that at critical point, the fluctuation will be significantly enhanced. So the only way you could detect there's a critical point here is to understand the signature of the fluctuations. Okay, and then that will be a smoking gun for the critical point. Yes.
How do you change the chemical potential? How do you change the chemical potential?
Yeah, the way you do it is that you make the ignite at no energy. So if you collide at very high energy, and then they just collide, and then essentially in the middle region they're all melted. There's no barrier left in the middle. And if you collide them at a low energy, then in the middle there's some kind of barrier left, and then you have higher barrier. So yeah, you just change the energy. It's an energy scan. It's an energy scan of this collision of yeah. So we do this scan.
How do you control both the chemical potential and the temperature? How do you control both the chemical potential?
Yeah, you just arrange the energy. Of course, it's hard to predict. Then you just see what you get. But when you collide at low energies, for example, in the previous experiment which they collide at low energies, you do see a significantly higher kind of potential. Of course, temperature will also be lower. Temperature will lower, but maybe enough to detect it quickly. Okay. But the key is that you need fluctuation to detect this quickly. And fluctuation is key. Okay. So also finally, the currently formulated hydrodynamics is actually a logical theory. So as I said, the equations of motion are just energy momentum conservation. But the input of this energy momentum conservation are, say, you have to express energy momentum in terms of these, in terms of those quantities, and that requires significant logical input. Okay, requires significant input. But as we also argued, that the hydrodynamics will be the low energy effective theory, universal low energy effective theory for all quantum many body systems. Okay? Given such a universality, then we should be able to derive it from first principle. Okay? First principle. And this first principle derivation should also be able to help us formulate it in terms of some kind of action principle, rather than just equation motion. So once you can formulate in terms of action principle, and then of course then you can incorporate fluctuation systematically. And so this course that we look for some kind of first principle formulation of hydrodynamics. Okay. Really formulate as some kind of generally low energy effective theory, rather than as a logical theory. Okay, so actually search for action principle for the dissipative hydrodynamics is actually a long-standing problem that dating back at least to Hackloss in 1911, which he actually managed to write down ideal fluid version of the hydrodynamics, ideal fluid action just without dissipation. And over the years, many people have looked at this. So these are some reviews, etc. And also during the last decade, due to various interest from the particle physics, cosmology, and also from string theory perspective, actually there are also many interests, renewed interest in this question. Okay. So for the rest of the talk, I will just outline some of the main ideas behind our recent series work, which we actually we solved this problem. Okay. And the discussion is a little bit theoretical, okay, it's a little bit formal, and so I try to be so I will just try to outline some main ideas. And so these are developed with two of my former students, Paul and Michael, and also work with John. And there are also some related work by Hale and so also Amos and Natalia and worked on. Okay, so the basic framework is what we call the effective field theory. And the basic idea of the effective field theory is the following. So let's consider a full path interval of your system. So this is the exact description of your system to a full path interval. And now you identify, but since we are interested in the low energy physics, okay, we are interested in physics at long distance and long time scale. And then you try to identify those degrees of freedom, which are only relevant at low energies, okay? So what you will do is that you will just integrate out all the rest of the freedom, okay? Exact those degrees of freedom. Yeah, you integrate out the rest. And then you just get the path interval only of the low energy degrees of freedom, and with a low energy effective action, okay? With a low energy effective action. And so this low energy effective action will capture, will be enough to describe all your low energy physics. Okay, so this is the basic idea. But of course, this is easily said than done. And this is always impossible, except for very, very simple systems. For the general many-body systems, this is just not possible. Okay? So the general strategy has been developed in particle physics, in this matter, in many fields during, say, last half century, is that we actually don't need to obtain this non effective series. We don't need to do any direct computation to do this path integral. What you can do is the following. So now you have identified the degree of freedom, okay? And what you can do is just identify the symmetries and constrain this non-effective action to satisfy. And then you just write down the most general effective action to be consistent with those symmetry and constraints, okay? And then that will be enough to describe your knowledge physics. And this will be a first principle because you only identify the degree of freedom and the symmetries. Then there's no other phenomenological input. Okay, there's no other phenomenological input. And that's how we derive the pion theory. Okay, and that's how we derive the theory for superconductors. And that's how also how standard model works. Okay, how standard model works. Okay, so here are some challenges to carry this out. So the first, this is a dissipative system, and there's a standard law that the dissipative systems don't have action principle. And for example, this is the simplest case. If you have a particle move with friction, can move with friction, and we were told in high school that we cannot write action for this. We cannot write action for this. And the second is what the dynamic variable you should use. Okay. So the standard hydrodynamics use, say, the particle density, local temperature, and velocity, etc. But turns out they are unsuitable for action principle, for first principle formulation. And there's a simple reason for it. So if you look at the equation motion for the hydrodynamics, they actually express in terms of the first derivative of those quantities. Okay, first derivative of those quantities. And we know if your equation motion is expressed in the first derivative of those quantities, then actually this is not a fundamental formulation. So the analogous situation is E and N. So when you write down the Maxwell equation in terms of electric and magnetic field, it's only first derivative in the electric and magnetic field. But if you want to write the action principle for it, you have to go to the potential. You cannot use the electric and magnetic field as a fundamental variable to pass. Okay, so here we have similar situation. Okay, here we have similar situation. So here one needs to look for the counterpart of the potential for the electromagnet. Okay, and then last we have to identify the symmetries. What do we mean by a fluid? Okay, in principle, what symmetries? The symmetry should specify what you mean by a fluid. Okay, what do you mean by a fluid? Okay, so that's the thing you have to do. Okay, good. So now for the question of the dissipation. So it turns out, even for classical systems, okay, for dissipative system, if you want to write down action, the natural thing to do is not to do it in the classical physics, which actually is not, it's not easy to do. You can do it ad hocly, but this is naturally resolved by quantum mechanics. As follows. So here you are interested in the dynamics in some kind of state, some kind of non-equilibrium state. Okay. So now when you formulate your quantum system, when you do path integral, you actually cannot do the ordinary path integral, because of the state involves like following. For example, if you take a density matrix, a generic state, and then involve, say, with U and U dagger on both sides. So actually, when you translate the path integral, that's put one into two contours. Okay. So now, if you're interested in some expectation value in this state, and then you need to take a trace, and then you can just close off on the one end, and then now you have to do a so-called closed time path like this. You do the path integral from mass infinity to path infinity, and then come back. Okay, and then come back. And so this is normally called the closed time path or single cabbage control. So now, if you formulate the system on such a control, and then you do the non-effective action, then the dissipation can be naturally incorporated. Then you can actually easily get action with dissipative terms. Okay, so the simplest example is just Brownian motion, which already was understood from remember the Feynman in the 60s. And so in the Brownian motion, you have some heavy particle, and in the bath, and now if you put the whole system on this kind of double contour, and you integrate all the parts, and then you get the action, dissipative action for this heavy part. Okay? And then if you're interested in the classical regime, then you just take the classical limit. Then you just take classical limit. And that gives you a natural formulation, even a classical dissipative action. It's better to start with the quantum regime. Okay? So now, let me also quickly mention how to do the dynamical variable. So the idea is the following: you have to identify universal variables associated with energy momentum conservation. Okay? Because of the fluid, because that's the universal non-distance physics. And so we have to identify such variables for that. And so the trick. So here there's a trick. Again, you make system more complicated. Okay. Previously for dissipation go to quantum. Here, even you are interested in the flat space physics. Now we put the system in the curved space time. And now because energy momentum conservation, the physics in the curved space time become non-trivial, because now when you put the system in the curved space time, because energy momentum conservation, then actually the system should be diffeomorphism invariant. So what this means is that the physics should not change on any coordinate transformation because energy momentum conservation. Okay, so this is a smoking gun of the energy momentum conservation, is that the coordinate invariant. Okay. So now to capture this using some dynamical variable, then now there's a simple mathematical trick. So now you can just promote the space-time coordinates into dynamical variables. So previously you have this space-time coordinate, so now I just promote into dynamical variables. And now when this becomes dynamical variable, then I have to integrate them in my path integral. So now you just integrate all possible coordinate choices. And then now you have naturally realized this diffeomorphism. And the integration of this kind of variable, and now will be equivalent to the energy momentum conservation. Okay? So now we identify the dynamic variable associated space-time coordinates now as the fluid variables. Okay, as the fluid variable. Okay, so then you can show if you do that, the equation of motion of x view indeed are equivalent to energy momentum conservation. But there's one small catch. So previously, these are just space-time coordinates. And now if you want to promote it into some dynamical variable, this dynamic variable have to depend on something. Okay, so now you have to actually introduce. So here now I have introduced some extra coordinates. Okay, so now you have to introduce a new space-time. Because when you make a diffeomorphism conservation, this has to be function of something. So that means you have to introduce a new space-time with some new coordinates. Okay? So now it seems like in order to describe hydrodynamics, now you actually have to introduce a new space-time. You not only make your previous space-time to be previous space-time coordinate to be dynamical, you actually have to introduce a new space-time. And now you actually have to do it in a double copy because as I mentioned, in this closed time part, you have to be two of them. Okay? So now the dynamical variable have two copies of this kind of emerged somehow new space-time. Okay? And this looks like highly bizarre from first sight. But now you immediately see, look at it, you see, this is precisely just Lagrange way to describe fluids. So remember, and what we can interpret is that this coordinate, new space-time we have introduced, are simply can be imagined as labels of the individual fluid elements. Okay, and now you can slightly generalize the sigma 0 to be interpreted as internal time associated with each fluid element. And then now you have this picture. So now you have fluid space-time label each fluid element and their time and their internal clock. And then mapping to the physical space-time that tells the motion of each fluid element. So this is precisely the physics which we track each fluid element. Okay, track each fluid element. And so in a sense, using this modern way to think about diffeomorphism invariance, okay, you essentially have just recovered this Lagrange description. Okay, and so this indeed tells you this must be the right description. And then from here, you can again just derive the velocity effect. next slide, we're not going there. So I'm actually almost running out of time now, so I will be quick. So now we also have to specify what you mean by this is a fluid. Okay, this is a fluid. So now we have a theory defined on this so-called fluid space-time. The sigma I label the fluid element, and sigma 0 label internal time. Then what we want to do, so now we want to introduce additional symmetry. So we want the system to be invariant under the relabeling of the fluid element. So if you have a fluid element, they can move each other freely, of course, you can relabel them. But you can only relabel them at a single time, okay? Because once they start moving, you cannot relabel them anymore, okay? And so this is one of them. And the second is that if you follow the trajectory of each fluid element, you should be able to reparameterize their internal clock, okay? You should be able, so that's that. Okay, so if you do that, and then that's the symmetry you impose, okay? And then let's define what you mean by that. So if you do that, then you find that this actually precisely recovered. So it turns out this symmetry indeed do magic for you, and you just recover the standard formulation of hydrodynamics. Those phenomenological relations to express the stress, to express your energy and momentum in terms of velocity, etc., they just can be recovered from those symmetries. Okay, there are a few more things, and in particular, the full nonlinear fluctuating hydrodynamics actually now encoded, now becomes a differential geometry problem. Okay, and then you just enumerate the curvature, environment, etc., and then you just have the hydrodynamics. So then in the usual situation, this would be the full story. But here, actually, the story is far from over, and there's still a few things we need to do. And since I'm running out of time, so I will do them quickly. First, since this is a real-time physics, they will be constrained from the real-time evolution. Okay, from the real-time evolution, which in quantum mechanics they usually do. So that actually put a constraint on your system. So you can actually prove that any effective action you obtain, that by integrating out something with freedom, they always satisfy the constraint from the vitality. So you have to impose it. Okay? And the next thing you have to do is that, as I mentioned, the hydrodynamics consider long-distance physics. Then for each fluid element, it's actually in the local equilibrium. Okay, so that's a very important condition. So for the standard formulation of hydrodynamics, you have to impose this local equilibrium by hand. So that means that you have to by hand impose the first law, second law of dynamics. You also have to, for the time reversal. For the time reversal system, you also have to impose the on-site relation. So we're not going into detail here. So here it turns out those phenomenological constraints can actually achieved by just imposing a first principle Z2 symmetry on the system, which we call the dynamical chemistry. And then by imposing this Z2 symmetry in your action, then you automatically recovers first law, second laws of dynamics, etc. And you also get various other things, nonlinear outside relations, local fluctuating dissipation relations, and also you can do proof of second law, etc. And finally, when you formulate such effective theory in the path integral, you also have to specify your precise integration measure or your path integration measure. Okay, and that affects your if you want to do loop physics to fluctuation, that will affect. So now you have to specify the path integral integration measure of the hydrodynamic theory. So it turns out here again there's a simple mathematical trick. It turns out the integration measure can be conveniently captured by introducing some anti-commuting variables. Okay, introduce some anti-commuting variables and introduce some so-called VST type of symmetries. So this symmetry will transform, say, this anti-commuting variable to your standard hydrodynamic, to your bosonic variables, and etc. And the square of this transformation is 0. And then it turns out the combination of this VST symmetry which you introduce in order for the integration measure and this dynamical chemistry symmetry introduced for this local equilibrium, then combined actually leads to a new divergent fermionic symmetry. So now you have two fermionic symmetries now. You have this VST symmetry, then you have a new fermionic symmetry. And turns out these two just commute into a space-time translation. And this is precisely just like in the supersymmetry. And actually, this is actually now a supersymmetric system. Okay, a supersymmetric system. And this is actually generalized to many previous observations of supersymmetries in stochastic systems. Okay, stochastic systems. To a full nonlinear non-equilibrium systems. Yeah. So here just tell you some smoking gun, and in the end, what you find. Just some results, some slogan, and the hydrodynamics with the classical statistical fluctuations is actually in the end described by supersymmetric quantum field theory. And this was, even though it's a classical statistical fluctuation by quantum field theory, and the H bar in this quantum field theory essentially is what we normally see, what controls the statistical fluctuations one over the interdependence. But now, if you want to include the quantum fluctuations, the story is more complicated because now in this theory already. It's already a quantum field theory with H bar. H bar effective. Now you have to add another H bar, and somehow it's a quantum deformed quantum field theory. Okay, and so that just tells you that the quantum correction to hydrodynamics is actually highly important. It's highly important. Okay, so finally, we expect to have a such theory should give you many applications, and some of the important physics I mentioned earlier. As I just mentioned, and let me just finally highlight just one aspect. So turbulence, of course, has been a very important problem for many years. And since 1950s, this Soviet school of Kolmogorov, they discovered that to study turbulence is actually important. Turns out it's much more transparent not to follow individual turbulent flow. That you don't learn much. If you want to extract universal information about turbulence, what you should do, you should look at the collections of turbulent flow. You should look at the ensemble of turbulent flows. And then you should look at the correlation functions in this ensemble, the velocity correlation function, etc. So already in the 1950s and 60s, they were marveled at. Somehow this way of describing turbulence is very similar to what people do in quantum field theory, okay? But they could not find any connection with quantum field theory. They could not find any connection to quantum field theory. But now we have a framework which formulates the hydrodynamics using quantum field theory now. So now maybe turbulence can be described by some kind of fixed point of this quantum field theory, because we know the turbulence corresponding to some scale invariance, etc. And so it's natural to expect that the turbulence indeed just can be described by so the previous ensemble average then can be just replaced here by statistical average and exception. Yeah, so I'm very hopeful maybe this can open some new techniques for dealing with turbulence that will stop it.
I don't understand the relevance of an energy momentum.